Good afternoon. I will present a proposal for a high-precision particle astrophysics detector to explore a new window of the universe based on antimatter large acceptance detector in orbit, ALADINO. We are discussing here about fundamental physics and fundamental law of physics. And we know that thanks to the work done in space by agencies like ESA, we can explore back to the beginning of time, the very early moment of the development of the universe, while in location like laboratories in CERN with a particle accelerator, we are able to study the infinitely small phenomena of fundamental interactions. And the two studies together are eventually pointing to the very same issue of understanding the basic law of nature. Thanks to this joint effort, we are able to establish that the universe is made out about 73% of dark energy, 23% of dark matter, cold dark matter particles, and atoms, which is the matter which we are made of, only covering 4%, including photons. So dark matter in the universe can be compared to a jar with a very few edible candies, us, mixed together with a tremendously large amount of matter, which is totally invisible so far, except that for gravitational properties. Then there is another puzzle which is in front of us. What happened to antimatter at the beginning of the universe? Antimatter in the universe today is a big puzzle. It's a kind of a lost can. We know that at the beginning was 50%. We know that was a tremendous annihilation taking place at the very beginning. What is remaining is about a part in a billion. This part of the billion is what is around us, is the environment where we live, but there is so far no evidence why the corresponding 10 to the minus 9 of antimatter should have been disappeared, could be still around in ways and in combination, which we are not very able to explain. AMS, the Alpha Magnetic Spectrometer, operating in the International Space Station for now more than 10 years, was able indeed to find anti-helium-4 candidates, one part in 10 billion approximately, which is totally unexpected, corresponding to the current model of cosmic rays and the propagation through the galaxies. And events like that are very puzzling, because 100 years after the ES discovery, cosmic ray experiments in space are now providing very precise measurement. And as AMS has shown on the ISS, those measurements can bring in some very accurate observation of phenomena, which is extremely rare, but which are carrying a very heavy amount of information about the origin. In 7 years, AMS has collected over 120 billion of charged particles. And after AMS, the spectrum of electron and positron, the antiparticle of the electron, or helium, carbon, oxygens, and the various isotopes and elements are measured with a percent type of an accuracy. Few tens years ago, the distribution were measured with 50% accuracies. So we are entered for the first time the era of precision cosmic ray measurement, and we can try to grasp the type of information that only charged particle can provide to us. So the idea is to have high precision particle astrophysics using antimatter particle. Of course, this is bringing to a new frontier of being capable of observing a large amount of cosmic rays, extracting the very small fraction of antiparticle. Example, 5 in 10 to the minus 3 of positron, 10 to the minus 5 for antiproton, 10 to the minus 7 for antideuterium, 10 to the minus 9 or less for antihelium-3, and so on. So those are very tiny fluxes, however, they carry a great amount of information, since the origin of the antiparticle is intimately related to fundamental processes. There's nothing strange about that. Also, looking to light, we are selecting a small fraction of the information which carry some interesting type of signal on a background which is very largely dominated by other phenomena. Very similarly, we are now entering this era for cosmic rays, as we did in the past for light. An example of physics topics for a high-precision particle astrophysics detector is about the search for the origin of dark matter. The interaction between dark matter candidate creating normal particles can be seen as a diagram, which can be studied in different directions. The LHC can create, from the initial state at high energy protons, final state containing dark matter. Direct interaction of dark matter existing in a universe flowing through the Earth can provide scattering information in a detector located underground. And IMS, or an experiment like AMS, can study the annihilation of dark matter particle, creating final state containing very rare antiparticle like positron, antiproton, gamma. And AMS indeed has observed clear positron excess due to a source which is concentrated at high energy. The measurement is very precise and can be interpreted as a diffuse term plus a source term. And the origin of this source term can be speculated to be, for instance, due to a multi-element, multi-particle dark matter candidate, as well as other astrophysical possibilities. So how to solve this issue? There is a very big signal how we can solve this issue and extracting information from the presence of this positron peak. The presence of this positron peak is still compatible with the existence of an annihilation process of a dark matter particle, provided those dark matter particles have very high energy, above 100 or several hundred GeV. Please keep in mind that above a TeV or so, LHC cannot really explore the various models because of lack of the energy in the phase space. So Aladino is designed to clearly identify the origin of the AMS positron excess, because it's going to study in particular at high statistics the falling down part of this electron peak. If this falling down is very rapid, very quick, this corresponds to a phase space, a limited phase space with annihilation of dark matter particle, and that will be a smoking gun for detecting dark matter candidate. If instead are different physical phenomena causing this peak, like single pulsar, multiple pulsar, broken power law, and so on, you don't expect such a clear falling down, and a clear edge, and that would be the resolution of this issue where this peak is coming from. This will be also studied in great detail, use antiproton, anti-deuterium, anti-helium, because all those antiparticle, very rare antiparticle, are very much sensitive to the presence of a source due to dark matter annihilation, following models which have been studied over the last several years. So the statement of this idea, this proposal, is that high dark matter masses above 1 TeV, which will be compatible with the limit existing from the LHC, and also with direct searches, could be studied by precision measurement of the detailed feature of the energy spectra and arrival direction of cosmic ray positron and electron at the TeV scale. And these measurements are needed to clarify whether dark matter annihilation or new physical phenomena are the source of the anomaly observed in the positron fluxes by AMS. The second example of physics topic for high precision particle astrophysics is the disappearance of nuclear antimatter. As I mentioned before, we clearly don't understand where the 50% of the remaining particle after the annihilation went, the antiparticles. Those studies in searching for antimatter in the universe have been done in different laboratories, both searching for traces of baryogenesis, like new symmetry breaking of proton lifetime, both failed, or direct searches, like AMS in space, and pushing towards measurement of the direct observation of anti-helium 3 and 4 or more heavy elements. All anti-deuterium candidates of AMS are observed 1 or 2 in the first 10 years of operation. Anti-helium 3 candidate, both anti-deuterium and anti-helium 3 are expected with the statistics in certain models, but the ratio of helium 3 to helium 4 to anti-helium 3 to anti-helium 4 is 2 orders of magnitude above the expectation by various models. And similar, the presence of a few anti-helium 4 candidates in AMS is totally incompatible by several orders of magnitude with respect to the existing model. So they call for new physics. But of course, this should be confirmed by much higher statistics by a detector operating with a different characteristic than AMS for a longer time with much larger acceptance. This is why we considered Aladino, which will have a 2 order of magnitude more event period than AMS, allowing for an ambiguous determination of the antimatter signal of AMS, measurement of the mass energy spectrum of this distribution, and searching for higher Z antimatter. And Aladino is a cylindrical detector having an acceptance close to 4 pi, as a sophisticated calorimeter at the center, surrounded by silicon detector, and placed inside a very strong magnetic field by superconductor. Those are the values, parameter defining Aladino, an acceptance of about 10 square meters per radiant, a maximum detector rigidity of the spectrometer 20 TeV, a calorimetric depth of 61 X0, and an energy resolution between 25 to 35%, and 2% for electron and positron. Aladino with respect to AMS2 in 8 years would be a factor of 100. And if it is operated only with the tracker, it can be also additional factor of acceptance. So it will be the ultimate response to the study of antiparticle in space, making precision measurement in a region where so far AMS has made a breakthrough with the first observation in the last 10 years. Aladino has a technology path based on a sophisticated silicon strip or pixel detector, cube crystal calorimeter, superconducting magnet based on YBCO magnet developed at CERN, low power cryogenics developed to the collaboration with the CSA Clay, electronics, which is now getting much more reduced power consumption and many more channels to make a very pixelated detector, and thermal shields which can be passively protecting the superconducting magnet operating at about 50K. Operating this detector in a very quiet condition from the thermal point of view will be an important design goal, and operating at a Lagrangian point L2 will be the best place to operate exogenic superconducting magnet like the Webb Space Telescope. And Aladino has also a pathfinder strategy by 2030 to develop a smaller version with a reduced magnetic field, 10 times less, some collecting area, having as a physics goal the nuclear antimatter up to 100 GeV, still a first-class science, and having as physics goal also the precision GeV energy of cosmic ray physics, and 2 tons of weight, and the full version, which is a full magnetic field, 6.5 tons of weight, operating the Lagrangian point, making nuclear antimatter study up to 1000 GeV, and dark matter in the multi-TeV range, and the composition of cosmic ray in the multi-10 TeV approaching the CNI. The core team member which has started this study include all the cosmic ray physicist and gamma ray physicist from AMS1 to Pamela Fermi, Dampe, Arina, Agile, and CS01 that in Europe have led this study of precision cosmic rays, and they are distributed over various countries. And with this, I finish my talk, and I wish you a good continuation of this interesting conference.